So we are interested in multivariate Ornstein-Uhlenbeck processes as like a linearized stochastic system, as a quintessential simple linearization of a given nonlinear dynamics with stochastic terms, but in particular with the study of heterogeneous temperatures. So the role of different temperatures, and I guess in the context of financial markets, that's naturally volatilities that will change the way different variables feel the noise and may change with noise. So let's take another title, and which could be for a different kind of lecture about this result, which is will a large heterogeneous system be stable, which I think resonates a bit more also with this session. And the point is that, yeah, we want to study how large systems, so because we'll need some kind of large n limit, and heterogeneous in the sense of heterogeneous temperatures in this case. And I will add another actual adjective, which would be stochastic. So it's not strictly deterministic. We also have these stochastic terms, and that's how we can define heterogeneous temperatures. And I'll keep another second with the slide because you can have the QR code, because we just uploaded the paper literally yesterday on arXiv. So if you want to follow it while I speak. So briefly, I will mention the role of random matrix theory in time series analysis, and that's one of the motivation for studying this, and in the context of covariance in time series, in complex systems, and specifically in financial time series, as we've seen in the previous talk, and in particular, the role of the multivariate Ornstein-Uhlenbeck model as a simple linearized stochastic model that allows for stochastic dynamics and couplings and some kind of degree of analytical results. And in particular, we'll move on to spectral theory, so the ability to actually predict the covariance spectrum, in particular also the lab covariance spectrum, so the dynamical properties of the systems, and in a specific ensemble which we identify, which is the reversible Ornstein-Uhlenbeck ensemble. And the point is that, which we identified during this research, is that not only we are computing the spectrum and kind of show that it kind of represent and have like properties that are in common with real data, but also with the spectra, we can fully characterize the phase diagram and the stability of the system, as also previously pointed out in the case of deterministic systems. So by computing the spectrum, we're not only kind of identifying empirical properties, but also have control on the stability of the system. There is a huge literature on random matrix theory, which I won't bore you with today, but if you're interested, I'm very happy to discuss all these kind of other ensembles that have been working on random matrix theory, not strictly with a dynamical process in mind. So many of these models have been implemented in the context of quantum physics or in the context of random matrix theory without a dynamical process, so like a correlated in time process that has some kind of continuous of discrete dynamics, while we specifically try to start with a dynamical system with some kind of random couplings and kind of come up with a random matrix ensemble as a consequence. And there are lots of different kind of applications in this case. One of like a prominent application is in the context of, for instance, of correlation matrices in defined and data mining, like clearing the correlation matrix. So there is a huge literature also on that, but it's also, there are tools for spectral partitioning of graphs, signal reconstruction, and factor analysis. So random matrix theory, let's say, has a lot to say in data science, and in particular in the context of covariance in financial time series. There are some kind of famous papers also from early 2000 on the spectral properties of financial markets. And this is probably, if you study any kind of covariance matrix and compute the spectrum, you've seen pictures like this one, where you can identify some kind of outlier eigenvalues. This theory is also very lately, in the last few years, has been also used in machine learning to understand when the generation error of large network models, neural network models. And in particular, one property that was not really understood by the models implemented was this IPR property, which you may have heard a bit less about, because you can compute the spectral density, but also the IPR as a characteristic behavior with the eigenvalues. In particular, you have some extreme eigenvectors at the edge of the spectrum, both for small eigenvalues and large eigenvalues, which appear to have less important components. In particular, they are characterized by a few of the main stocks, which is kind of related to the some asymmetry and heterogeneity in the relevance of different stocks. Did you wish this was also one of the motivation of this model? But we actually found out that an even more prominent motivation for this model is the possibility of understanding criticality in a linearized system and understanding how at the stability transition, even in this generalized ensemble, you can find criticality and the emergence of power laws, even in a Gaussian, let's say, simple system. And these appear, as you probably have seen in the last few days, in economic models, neural models, and so on and so forth. So this is the model with the linearized dynamics plus noise. That's an important part, of course, of our study, with a positive matrix for the noise T, which can be decomposed in a BB transpose. And this is a typical picture that you can get by simulating this kind of processes with random couplings. But of course, you have to guarantee some level of stability for the large convergence of the model. And this model actually was found some time ago that can predict the IPR behavior that I was talking about. So it's relevant empirically, let's say. And also there is a CPR like properties that can be obtained by this heterogeneous temperature. So it's not completely arbitrary to introduce this heterogeneity. But in particular for this talk and for this result is the fact that you have this Silvestre-Lyapunov equilibrium relationship that you may have seen already in Ornstein-Uhlenbeck processes, which again makes them interesting in the sense also that we can obtain analytical results for the covariance stationary matrix. But this is like an equation in which we cannot really have an analytical solution in S. We can solve it like also quite efficiently, but we don't have an analytical form for S as a function of A. What we do in the case of reversible condition, which is why we kind of focus on this case, where we can study the system where S has an explicit solution, which is A minus 1 T. And bear in mind, in this case, A doesn't have to be symmetric. It just has to be reversible. So that's the point. So A can be non-symmetric and heterogeneous, the system. Actually, we found out that this means that we can identify a transformation of the variables which will translate the system into a symmetric and homogeneous system. So in a way, we are in the universality class of symmetric Gaussian couplings, but with the possibility of introducing heterogeneous temperature and study that case in this ensemble. So another reason why this ensemble was particularly relevant for us, and we identify a general way of decomposing matrices in reversible Ornstein-Uhlenbeck processes, is the fact that we can really have the solution for S and the solution for the lag covariance S tau in a special transformed symmetrized system. And in particular, we have a trick, theoretical trick, together with the replica trick I'll present in a second, which is studying the precision matrix. So the fact that instead of studying the covariance, we can study S minus 1 when possible, which is the inverse of the covariance. And actually, as you can see, the analytic formula for that, it's slightly easier in our ensemble so that we can then proceed with the analytic calculation with a bit more ease. And the main result, which is kind of like a very general like approach in statistical physics of disordered systems, is studying the green function and the spectral density connection to the green function, which essentially introduces a partition function. So we study the statistical mechanics of this ensemble. And we can solve that. We can compute these averages over the distribution of couplings and obtain general results on the spectral density. These are like known approaches for computing these partition functions. And in particular, we have to introduce, to compute this logarithm that you see above, we can introduce a set of replicas, and we can take a limit for replicas going to 0, which is the replica trick, and actually have analytic results for the spectrum of the covariance matrix, in particular the precision matrix in this case, for this dynamical system with randomized couplings and randomized temperatures. And in particular, we find this very simple kind of result, which has asymmetries with other results in the context of random matrix theory. But you see that when you introduce this kind of heterogeneous temperature, eventually we end up with a spectrum which, if you're familiar with the Wishart ensemble, it's very similar to the kind of saddle point equation, but with a like G squared function of the temperature. Brilliant. That provides the results. So let me get to the results, actually. So this is the exact, if you were wondering, the exact form that can take in our system. In particular, we choose G of T as a power of the temperature. And in particular, this has a number of interpretations which we provide in the paper, where we explain that this kind of relates to the fact that we are renormalizing the couplings with respect to the temperature of my neighbor, in a sense that maybe some highly volatile neighbors are less reliable, and then the couplings that I get will be diminished, in particular in some cases. Now, what's interesting, and I want to get to the main point, so we can provide results on the spectral density of the covariance, of the lag covariance in this ensemble, so to generalize all these results. And we can also study criticality and marginal stability. So the fact that when we approach the unstable state for these matrices, we end up with this power law dynamics and criticality at the marginal stability threshold. And in particular, which is novel, I guess, in the context of this dynamical system and in the context of like heterogeneous temperature, is this kind of plot. So the fact that when we are changing for a fixed average temperature of the system, the heterogeneity will move the transition. So the threshold for the stability is not only dependent in a way by the coupling in itself, but also by the heterogeneity of the distribution of temperatures. And of course, this is connected with the fact that we have a reversible condition and constraint that is enforcing this transition. So if we look at the variability over delta, of the stability, we have a phase of stability and a phase of instability just by varying the heterogeneity of the system. So that's what we observe, and we see that we reach instability not by varying the couplings in itself, but by varying the heterogeneity of the temperature. So this is of relevance for us in this context also of instability of general Gaussian inference for the general inference model of Ornstein-Uhlenbeck, not only in the reversible case. And I guess it falls for me in a more general research agenda in the context of stochastic process inference from plane series data, which we're approaching also with physics-informed neural networks. And we have a paper that's been presented at ICML AI for Science. Thank you very much for your attention, and welcome questions.